Thank you everyone for joining me. Hopefully we've got some non-semiconductor people in here, even though the topic is mixture experiments for dry wafer etch processes. What I plan on talking about today is a very, very common situation that occurs in multiple industries, and that is when you're dealing with a mixture experiment in the context of non-mixture factors in your design. So hopefully folks can abstract away from the semiconductor focus of this, but let's go ahead and get started. So in this particular experiment that we're going to look at, we have a dry etch process. There are 8 factors that we're interested in. 3 of those factors are part of the mixture, and those are our 3 process gases that we're going to vary. And by the way, so for those folks who aren't unfamiliar with wafer etch processes, we've got a chamber and we flow a fixed amount of gas into that chamber. We want to vary the ratios of those gases to etch the wafer that's in the chamber. So that's going to be part of our mixture. In addition to those 3 mixture factors, we're going to have 5 process factors also that we're interested in looking at: power, pressure, temperature, time, and total flow. In this particular experiment, the investigator was interested not only in the ratio of the gases, because that makes a difference in terms of how quickly and how well you get this etching process, but also the total amount of flow. One of the things people discovered early on that is it really matters. Those ratios matter, and the amount of gas that you flow inside these chambers matters as well. So we want to be able to look at both of them and say, well, if I increase the gas flow but keep the ratios the same, that will or won't make a difference. Okay, so we want to look at both in this particular experiment. Now, one of the other things that we realized is that in order to work with a situation where we wanted to work with total flows and gas ratios, and we wanted to be able to make them as independent as possible, it really was best to use this mixture design. Now, in the past, there have been other approaches for designing these types of experiments, and they're quite difficult in that what we do is we do things like create slack variables and fix one of the mixture factors, and it's very, very complicated. The great thing is that with the custom designer, JMP allows you to do that much more easily. So you don't have to go through all of these machinations to be able to design your mixture experiment. Okay, so a couple of other things that were really important, and for those folks who do work with etch processes, you can relate to this. One is that the 2 of the gases we wanted to fix between an upper and lower ratio. So our gas A and gas B, we wanted to make sure that it was no less than half of gas A to gas B, and no more than 3 to 1 for gas A to gas B. So that was one of the other constraints, and I'll show you how you add those constraints into the design. The other aspect it was that 3rd gas C. We wanted at least 10% of the total gas mixture to be gas C, but no more than 25%. And again, very easy to do with the custom designer. All right. So that gives you some idea in terms of the overview of the experiment that we're trying to run. So what is a mixture design? So for those folks who are brand new to mixtures, let me explain a little bit what we've got and some of the challenges that we have with these mixture designs. So anytime I'm dealing with an experiment where the quantity of 2 or more of my factors have to sum to a fixed amount, and it's usually 3 or more, but here technically it could be 2 or more factors. Anytime that has to add to a fixed amount, then we have a mixture experiment. Okay. Now, with this particular experiment that we are dealing with, one of the other additional complications is that we've got non-mixture components. If you were to go to the statistical literature, again, this is something that until the advent of something like the custom designer was very difficult to build these types of designs, because you had to treat this almost as 2 experiments that you had to marry together. Now with the custom designer, you don't have to worry about that. Much easier to have these non-mixture components. Now, one of the things that I tell people to make this idea of dealing with some of the complications of mixtures designs a little bit more, a little bit easier. Think of the goal of this experiment to focus on prediction. We want to emphasize prediction over factor screening. With mixture components, with these mixture factors, we never really remove them from the experiment. So we're not doing a type of screening where we might get rid of one of these gases, one of these three gases. And in addition, I am going to argue that it's good to think of even the even the non-mixture components as being things that I don't remove from my experiment. I fix them at a given level, and my focus is not on saying whether or not something is significant or not significant. The focus is going to be on using the profiler within the jump report to be able to predict where my what my responses will be given certain settings. Now, technically, one of the reasons we do that is the mathematics behind building and analyzing these designs. But for the sake of simplicity, I think it's sometimes it's very helpful to think of this as a type of design where I'm going to focus on prediction and not on factor screening, not on screening the components of my design. Okay, so let's talk real briefly about some of the challenges that we have with mixture designs in general. So one of the biggest challenges is that because I have to fix, in this case, the total amount of gas that I'm flowing into my chamber, or in general, I've got that fixed amount of either by weight or by volume, the fixed amount of mixture components that have to add up to a given value. So because of that situation, things are highly correlated and harder to estimate. So sometimes what needs to happen is I just need more runs to be able to get a better estimate, but that's one of the difficulties and one of the challenges. One of the other challenges, and one of the reasons I believe it's much easier to think of these types of designs as being focused on prediction rather than factor importance, is that there's a lot of confounding that occurs. So for example, if we were just to consider an experiment, let's say where we only had those three gases and everything else was a set value. If we only work with those three gases, a lot of people would, let's say, if they weren't familiar with mixture designs, they would design it similar to a response surface design, where they would look at main effects, two-factor interactions, and quadratic effects, or square terms. With a mixture, you can't do that because of the confounding. As it turns out, those square terms are in fact confounded with main effects and two-factor interactions, so you cannot put both in the model. If you try to do that, in the custom designer, you would get a message saying that the custom designer could not put those effects into the experiment because of confounding, and it's going to remove certain things. So main effects, two-factor interactions, yes, but once you try to put those square terms in the model, you're going to have problems because of the correlation. In addition, if I am working with non-mixture components, I have correlation between, let's say, a non-mixture component and the two-factor interactions between that non-mixture component and a mixture component. So for example, in the experiment that we're working with, I cannot put both power and the power by gas A two-factor interaction into the model because they're confounded. Okay, so what I would like to do is I would like to show you some ways that we could get enough terms, enough effects in the models to get a good estimation given the runs that we have. Then once we do that, we're not going to worry about what the size of the parameter estimate, estimates mean, or how big the parameter estimates are, or whether or not they're significant. We're not going to focus on that. We're going to focus on prediction. Okay, so again, the important thing here is to focus on on prediction. All right. So let's go into a little bit more detail in terms of this experiment, and let's actually set this up as a designed experiment. In this case, we had two responses that we were interested in. We had etch rate, and in this case, we were targeting etch rate to a value of 100. And we also had the standard deviation, and we want to optimize both. We want to be able to hit that target of 100, and we want to be able to minimize the standard deviation of the etch rates over the entire surface of the wafer. Okay, so a very challenging thing to do in this context. We had, as I had mentioned, there are a total of 8 factors. Those very 3 at the bottom are 2 gases, and I'll get back to them in a second. The first 5 are if you've done designed experiments, no different than the way I would specify regular factors, non-mixture factors. I've got a high setting, a low setting. I want to keep within that those values. Now, with the gases, with our mixture components, I had mentioned earlier that we wanted to make sure that gas C was no less than 10% of our total mixture, no more than 25%. So that is in my that is in fact going to be in my design. That's going to be part of my setup. Now, one of the nice things about the custom designer is I don't have to worry about the math behind, well, what's my low setting for gas A and my high setting for gas A, and same for B. Given that I've also have these constraints that are going on, I'm going to say allow gas A to be between 0 and 1, even though I know I need some gas A in there. Same thing with gas B. I'm going to let the custom designer, the algorithm behind the custom designer, figure out what those values should be. And given that my total gas mixture, at least for C, is not going to go beyond 25% of my total mixture, and given that I fix the ratio of gas A to gas B to a certain amounts, I'm guaranteed to have some gas A and some gas B. All right. So I'm going to open up. I've actually saved those. I have saved those factor settings so I can load them quickly into the custom designer. All right, now we're going to also need to know a little bit about these constraints too. So what I've done, and when you have more time, I'll suggest that you could take a look at this. But basically, anytime that you have a situation where you can set up linear relationships between my factors, I can put in constraints in my design. Now, even though in this case I'm looking at the ratio of these 2 gases, I can turn this into, in this case, I can turn this into 2 linear constraints, and it's fairly easy how I do that. I start out with a ratio of my 2 gases being bounded between a low value and a high value. On step 2, I just multiply both sides by gas B, so I get the equation in line 2. In line 3, all I do is subtract gas A from either side. And from that should leave me with my two constraints. My first constraint is that 1/2 times gas B minus gas A has got to be less than or equal to 0. And the second constraint is that 3 times my gas B minus my gas A has got to be greater than 0. So those are my 2 constraints. And again, I went over that very quickly, but you'll have access to this journal, and you can, hopefully the math is relatively straightforward, and you could step through this fairly easily. Now, I've also saved my constraints as well, and we can relate back to these when we're setting up the design. All right. Now, if I were to have more than those 2 constraints, let's say I wanted to fix the ratio of my gas A to gas C, I could do that too, and I would do it in a similar fashion. Okay. So let's actually design this experiment. Again, fairly straightforward. So I'm going to go into the custom designer, and by the way, I had mentioned earlier that in the literature, there has been a lot of work done in terms of how do I do these types of mixture designs with mixture and non-mixture components. We have a whole bunch of classical designs that come from a lot of the books that you might find on mixture design. So just to let you know that they're there as well. I'm going to go with the custom designer because this offers me a lot more flexibility. Now, rather than having to watch me type everything in, what I'm going to do is I'm just going to load my factors in here. All right, and here are my factors. And again, what I have done in this case is I have made sure that the high and the low settings for all of my non-mixture components are set to where they are. I know I've got these hard constraints on my gas C, but I'm not going to worry about gas A and gas B. I'm just going to let the custom designer take care of that. We're going to go back. We're going to come back to the model part of this because this is the important part. This is where we're going to try to set up a design and not worry about all those constraints. And I'm going to give you some things that you could work with in terms of setting up these designs. All right. Okay. So that is our there are our factors. So let's actually load the constraints too. And again, if I wanted to get these constraints by hand, I would just specify the linear constraint. I would add them, and then I would use those equations that I showed you earlier in terms of setting up my design, where -1 times gas A times 1/2 times gas B, and that is going to be less than or equal to 0. I would add another constraint, and I would get that in there again, -1 times gas A, in this case 3 times gas B, and that's going to be greater than 0. And that's how I would set up the design. But the nice thing is once I've set this up, I should be able to load my constraints. Let me just make sure I've got my constraint table selected. And actually that looks like that is my incorrect constraint table. So I am just going to go with the constraints that I typed in by hand. Regardless, I can save those constraints to use later on. Nice to check the constraints, because sometimes if you've got a lot of mixture factors, if you've got a lot of constraints, you want to make sure that you've got some region left where you can actually run your experiment. Okay. So let's talk about how we're going to set this up in terms of my experimental design, so we don't have to worry about what's confounded with what. I'm going to actually treat this like we're two different experiments. One where I'm only going to look at the non-mixture components, and one where I'm going to look at the mixture components. So starting with my non-mixture components, I am going to look at, let's say, all the main effects in the two-factor interactions. Okay. Let me just hide that for a second. So I'm going to grab all of my non-mixture components, and I'm going to say interactions to degree 2, and then JMP is just going to add those. I'm going to do the same thing with my mixture components, and again, if I add those, there they are. Now, at this point, this is probably sufficient enough to be able to model a decent relationship between my inputs and my outputs. Keep in mind that I cannot cross my non-mixture components with any of my mixture components because they're confounded. I might be able to look at other relationships, but for the sake of simplicity, plus the fact that if you work in the semiconductor industry, you know that you usually work in lots of size 25. This works really well. In this case, I'm gonna stay with the default. I've got one additional wafer left over in this case. So I'm going to stick with this model. This should be sufficient enough to build in the relationship. And given that there is confounding, there is correlation between what I put in the model, how I've set up in the model, and a lot of the two-factor interactions that you might think that you need to add in the model. This should be sufficient for me to look at the relationship between my inputs and my outputs. I'm just going to go ahead and click design. And again, the nice thing about the custom designer is it uses the underlying algorithm to be able to come up with the best design, given that I only want 24 runs in this design, and that I've got both mixture components and non-mixture components. All right. Now, what I would do at this point is I've got my design. I've got my design here. I would probably save my design to a table. So I'm going to make my table. A couple of steps that I haven't done in the data set we're going to analyze, but certainly things you're probably going to want to do is you're probably going to want to take a look at, I mean, these are nice, but these values are in proportions of total mixture. So, but you probably want these in terms of SECM, the amount of flow. So what I'm going to do is I'm going to actually calculate, and I would do this for all three gases. I would calculate, I just selected those two columns. I'm going to say new column formula, and I'm going to combine them, and I'm going to say the product. So if you're not, if you haven't seen that before in JMP, that's a fairly new feature, these instant formulas. So now what I'm looking at is I'm looking at the actual flow in terms of SECM and not the proportion. So sometimes that's a little bit easier to work with. I would do that for gas B and gas C, and I would probably pass that to the operator, the engineer who's running the experiment, so that they wouldn't have to do the math to figure out how much gas there would flow. The other thing that I would probably do in these situations, and I'm going to go in, I'm going to delete that formula for a second. And I often run into this situation where, I mean, people will look at some of these values and say, there's absolutely no way. I mean, that is such, there's no way I can dial my gas flow to be that exact. In fact, I might only be able to get something that is, maybe 50. So I tell people that it doesn't, it might not be the absolutely optimal type of design, but there's nothing stopping you. If you cannot run that at 49, and then running it at 50 is an option. So another thing is that I might go back in, given how much control I have over the equipment, I might go in there and slightly alter the values that I have for my my gas flows. Okay, so again, that's important to do beforehand, because I'm going to use that in terms of the analysis. I'm going to use the actual values that I ran rather than the values that came out of the custom designer. Okay, so that pretty much that does it for the experimental design part. And if I wanted to add more effects to the design, I would do that in a similar fashion. But that's a real quick and hopefully easy to understand way to set up the design. Now, the next thing I want to look at is I want to look at analyzing this experiment. Now, the nice thing is that once I know the potential issues with what I can and can't put in the design, that should in fact help me with my analysis. So here I've got my experimental my experiment once it's been run. I've kept my gases at the in the proportions. I haven't included the actual gas flows in here, but here are our two responses. Okay, so what I typically do in this situation is sometimes sometimes I want to start from scratch. So I've actually removed the model that JMP builds in there. Sometimes JMP will pre-populate the model, and sometimes I don't want to work with that model. So I'm going to start out from scratch. And for the sake of illustration, I think it's very good in this situation to show you how I would actually set up this model. So I would actually set, now this is going to look very similar to how I set up the design. Okay, so start with the easy part. I'm going to put in my two responses. There's my etch rate, my etch rate standard deviation. I am going to put in all of my main effects to begin with. Okay. I am going to grab my non-mixture components and say factorial to degree. So it's just like I did when I designed it. And then I'm going to do the same thing for my mixture components, factorial to degree. That's almost identical to the way I set up my experimental design. So I'm going to analyze it the same way. Now, at this point, I've got a couple of options. I can completely completely take the tack that I'm not gonna do any screening. I'm not gonna remove any non-mixture component factors from my design. I'm just gonna run my model and I'm gonna focus on my my prediction. So I'm gonna go ahead and do that. I'm just gonna let me minimize a lot of these. So we just there we go. And I am going to skip right down to my prediction. And now I'm going to turn on, first thing I need to do is I need to turn on my desirability functions, turn on my optimizer. So you're going to find that next to the prediction profiler where it says desirability functions. Okay, that's step one. Step two, I need to make sure that when I look at etch rate is going to be targeted at 100. I'm going to hold down my control key and click. Okay, I'm going to set my target to 100. And I'm going to say match target. I'm not going to worry about the high and the low. And I'm going to control click on the desirability function for the standard deviation. And I am going to say minimize. And that's as easy as that's all I need to do to set it up. Now to actually optimize, to get my optimal value, I need to go back into the hotspot, back to the optimization and desirability and tell jump to optimize. Now, one of the things that you're going to notice is that there is a compromise. I have weighted both my etch rate and my etch rate standard deviation equally. Things like that can be controlled. I am not getting the absolute lowest in terms of my my etch rate standard deviation. It looks good. I am not hitting that target exactly, but I'm coming close. So that might be sufficient. If not, I can actually, if I were to control click, I can set my importance to a different value. So by default, both my etch rate and etch rate standard deviation are set to an importance of 1. If I want to make this twice as important, I could do that and then re-optimize. And there you go. Now you see that it's putting more emphasis on that etch rate. And I'm coming closer to that target. So that's the flexibility I have in terms of using that optimizer. So relatively straightforward, fairly simple because I only had two responses I had to optimize. Often you're going to find that you're going to need to compromise because I can't completely hit absolutely perfect values for all of my responses, but you can use that importance to be able to balance where I am. Now, one more thing I want to let me go back to my model dialog. So I had mentioned I just fit absolutely everything. I didn't do any screening. One of the things that you might consider is using something like stepwise regression. Now, you'll notice that when I use stepwise regression, what happens is that it puts these mixture components in there. It keeps them, it fixes them, it locks them so they cannot leave the model. I might, if I were to have, let's say, a relationship between a two-factor non-mixture component and a mixture component, then I might keep that in the model. But I'm probably going to want to keep these in the model as well. Okay. I would feel comfortable with using something like stepwise regression. And in this case, just about everything was significant. And let me go ahead and run the model. And then maybe I'd fine tune only removing those non-mixture components. Now, also keep in mind, even though I were to remove these for the model, I'm doing this for the sake of simplicity. The idea here is that power and pressure has to have some sort of setting. Okay, and it might be some nominal value. If it's not significant, I can set it to whatever value between my high and low setting. However, for the sake of making this model a little bit easier to explain to people, maybe to give to somebody to run, I am gonna remove anything that's not significant, that is not contained. It doesn't have one of these little carets here, that is not contained in a higher order interaction. So I might use that either via stepwise regression or via manually adjusting what isn't in my model. Again, these settings, even though I remove some of those two-factor interactions, I'm going to have the flow set at some value. If flow is not significant, then I could set it at anywhere between 80 and 120, but if it was significant, I would want to have it in the model. So regardless, I'm probably going to want to put that in the model. So couple of different options you can do in terms of fitting the model. Again, once the model is fit for both of my responses, I would turn on my desirability. I would turn on my profiler and my desirability functions and optimize in the same fashion. It's just a question of whether or not I want to clean up my model a little bit, maybe remove the things that don't have such a large effect, make it a little bit simpler, or just focus on the profiler. So that's what I have. Hopefully, this has given you, if you're new to mixture designs, hopefully this has given you a nice taste and feel for how you would set up a mixture when you have mixture and non-mixture components. My journal will be available, so you should be able to access that as well as the recording. And appreciate the time, and I hope this has been very fruitful for you. Thank you.